Welcome back to RISC-V emulation in a high-level language. We've been working on this project for quite a while now, and the code base has become a little scruffy around the edges, so I thought it would be a good time to start cleaning it up a little bit and maybe add a few more instructions because there's still quite a few left. Now, I decided to implement a bunch of new instructions off stream because I thought it might be a little bit boring to watch me do it. Maybe this was a mistake, but in essence what I've done is I've gone to the manual and copied the text of all the instructions summaries that you see here. I took that text, pasted it into my editor, and then I ran a few macros on it to generate automatic unit tests and assemblers for all of them. So after having done that, we have the full complement of the RISC-V instruction set, which is the general purpose instructions. And that was fairly easily done. So maybe I should have done that online, but I'll show the result. So this is the diff of that work. As you can see, first of all, I extracted a whole pile of new mnemonics, which are all the instructions that we haven't implemented yet. And then I created unit tests for each one of these instructions. So here they all are. And they're all fairly mechanical. Every place where there are 3 operands, we use the following bit patterns to represent the registers that we're operating on. And it turns out that there's even a few instructions that use 4 operands. So in any case, this resulted in a whole slew of new instruction encodings that I was able to automatically generate tests for. So for instance, here's the unimplemented branch less than unsigned instruction, which would compare 2 registers, and then branch if the result was less than if the contents of the registers are considered to be negative, or sorry, unsigned. And yeah, so here they all are. And then after writing those unit tests, I then proceeded to write the assemblers for all of those new instructions, and as you can see, it's all very, very mechanical. It's all just using a keyboard macro to convert the textual descriptions in the manual into actual C# code. And having done all that, I can now run all those tests. And let's hope that they do that they pass. And they do. I also wrote unit tests for all the emulation instructions. And I have those unit tests over here. They also all pass, but none of them are actually implemented yet because writing emulators does require individual attention to each one of these instructions. So you will see this ignore attribute in front of the method, which tells my test runner to ignore running these this test. So on a need-to basis, we will add new emulated instructions and write unit tests for them to verify that they are operating as expected. However, before I embarked on this, I decided I needed to clean up the code base a little bit because it's starting to drift a little bit, and it's always good to go back and take a look and see if you can recognize any patterns and perform any cleanups. Let's start with the assembler first. One of the things that I noticed as I was browsing through the code is that there are a few places where we're doing unnecessary work that could be simplified. And one of those places is instructions that have the funct7 and funct3 field. So there's quite a lot of them. So here's the main opcode of the instruction. It's always the lowest 7 bits. And then there's this field starting at bit position 12, which is the func3 field, which specializes the opcode into sub-opcodes. And then in some instructions, there's also a third field called funct7, which dedicates an additional 7 bits to specify the instructions even further. So it turns out that all of those three fields could be combined into one single sort of empty opcode without having to separate them into 3 fields. And this would allow us to simplify the code for the assembler. So, for instance, today when we are assembling the BEQ instruction, let's take a look at the code for that. So here we have the main opcode and then also the funct3 field of BEQ right here. So why not just combine these two into a single field? And that would save us a bunch of work inside of the ASMB encoder, because then we don't have to do this extra step. We can just provide the full opcode without a funct3. So let's go ahead and do that. Let's just remove funct3 and then make the assumption that the opcode will contain the funct3 when it gets passed into ASMB. And so if we go back to the places where it gets used, we will then change this so that there is a 7-bit, 5 bits, which is this immediate part. So we'll need the opcode and the least significant part, then 5 zeros, and then the funct3 part on top of that. So we can do another keyboard macro here, which is going to take a ASMB and then 0B followed by 7 bits. That's the first part we need to remember. Then a comma, and then as another 0B, and then 3 bits. And that should be replaced with ASMB followed by a 0B, and then the second capture group is the func3, so we want that first, and then 5 zeros, and then the first capture group. Alright, let's see what that looks like. We'll try replacing the first. Yeah, that looks pretty good. Then we got BGE, BGEU. Alright, so we have now replaced 2 fragments with a single full-blown opcode. Now let's run our unit test to make sure that we are still safe. And it looks good. We haven't broken anything. So having found that, we can do this with ASM-S also. So we'll do the same trick. We'll remove the func3 parameter. It needs to be treated the same way as before. So then we find all the places where we have ASM-S, and then we replace them in the same way. So now we have, oh, that's my mistake. Those need to be S's. All right. Okay, we keep on going. All right. So now we run all of our unit tests again. We're still good. Nice. Okay, so now we look for another func3. This is ASM-I instructions. We'll give them the same treatment. So if we find an ASM-I, then we replace it with this pattern. here, here, here. There's an awful lot of these. It's a very popular format. Okay, try running all the tests again. Oh, we have a build problem. Okay, let's try that again. Still working, lovely. Now let's find another funct. So here's ASM-R, which has both the funct3 and the funct7. So if I remove these two fields, then one of the fields needs to be shifted by 12, but the funct7 field needs to be shifted by 25. So let's think about that. So that's going to be 10 more bits. Let's just count the bits just to be sure. So we'll find the XOR, which is one of these functions that is using that encoding. We'll have 5 bits for RD, then 3 bits for the funct3, then 10 bits, which is enough for 2 registers. So we need to skip over 10 bits and then have the funct7 at the very top. All right, so to do this, we will have to find the ASM-R, and now we have a bit of a problem here. We cheated when we wrote these, and there's a lot of cheating going on. Let's see. Most of the ones that were added with my script are good, so we'll use this technique for the ones that have 0B prefixes. Alright, so let's use ASM-R, and then it takes 0B and then the 7-bit code. 7 bits like that. And now what we do is we change this to an ASM-R, where we take the last one, the funct7, followed by 10 zeros for the 2 5-bit register slots. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And there we go. And yeah, that looks good. Let's do them all. Let's verify that that all seems to work. Still works. And then we have, oh no, it doesn't work because ASM-R doesn't compile. So we'll need to change these so that they match the pattern that we're searching for. Let's find the next one. Oh, we'll clean that one up right there. And then let's find the next occurrence. This is another one. 1, 2, 3, 4, 5, 6, 7. This one is, why did it, I'll have to take a look at why that didn't get replaced. Because both of these look good. Do we have too many bits maybe? 0, 1, 1. Yes, we do. Okay, so we'll get rid of the leading bits like that. Right, okay. So let's replace. All right, no more errors. Now let's try building or running the tests. Okay, so we no longer have these little funct fragments in our assembler. I think we've done them all. Yes, they're all gone. And that's a small efficiency, but it will pay off later. Great. Now that we've done with this part, let's go over to the emulator and take a look and see if there's any way that we can clean it up. Let's see here. So looking at, this is the exec method, the sort of the heart of the emulator, and here we see some logic that looks it could probably be simplified or refactored. Well, what we could do is introduce a value. What does write register do? It takes an integer. So if we had an integer called value, and then instead of write register dist, we would say value equals, and do the same thing for these. What we're doing there is trying to minimize the code size, because the smaller the code size in general, the faster our code will be. So what this will do is it will trim down all these instructions, and then at the end of the switch statement, then we'll do the write register, and we'll take the destination register and use the value that was computed up there. Let's run the emulator tests. We haven't introduced an error, so that's good. So what else can we implement here? Well, here also is a lot of duplicated code. So what we want to do here, I guess, is do the same thing. We will perform the addition and the multiplication, but we'll do it and then write it to the register down here. So we'll say write register destination value, and then we can also, we'll introduce source one value, which is going to be the register. We don't have a reader register yet, so we'll fetch it directly from our array of registers. Although this is a problem because we're, oh no, we're not. No, we're good. So this would be source one. This would be fetching from source two. So now we can replace this with value equals source one value plus source two value. And then this one would be the multiplication. Nice. And then this will do the common thing. Let's run our unit tests to make sure nothing's broken. They look good. Okay, great. All right, so now we do the same thing for the immediate values. So it's going to look very similar. We can say, let's just copy this part. We only need one variable in this case, the source one, because these instructions appear to be all using the immediate, like the famous add I. So we'll just say value equals source one value plus im. And this one, in a similar fashion, is source one value. Nice. And then at the end, let's make sure we write that value. Good. This one doesn't merit refactoring. These are all the store instructions. They really can't be made better because these write byte, write words can't really be refactored in a useful way here. Well, we could, I suppose, we could do source 2 value equals registers a source 2, like that. And then we could use it here and here. and here. Not a big refactoring, but hey, maybe it could result in a tiny performance improvement. We'll never know. We haven't measured yet. But we will continue here. Now we have the branches. Okay, so all of the branches perform some sort of predicate or comparison, and then depending on whether the comparison was true or not, we want to change the next pointer to be the destination if the comparison was true, or if it was false, we just continue to the next instruction as normal. And we see a pattern here. So what I'm going to do is I'm going to introduce a Boolean variable called predicate, and then instead of doing all these if statements, we'll just say predicate equals, and then the computation, and then we'll move the branch part down to here. So if predicate, then perform the branch, like so. And then here we'll have to do the same thing, predicate equals. Notice now that there's no longer these branches everywhere. And we'll do the same trick here. We'll say var our source 1 value equals registers of source 1, and then register source 2 for source 2 value, and then we'll change this to source 2 value. Oh, no, source 1 value, and then source 2 value. And we'll do the same thing here. Nice, so now the code is a bit more compact. LUI we'll leave alone, JLR we will leave alone. Okay, system functions, there's not much to do to simplify them. Okay, let's run our unit tests again then and make sure that everything is still under control. And it looks great. So we didn't add any new functionality to the code. We just changed the implementation a little bit so that the following work of adding a few more instructions will be a little easier. And so let's commit our work so that we don't lose any valuable work or progress here. So let's just review the changes that we made. Yep, these are all the new opcodes. And then in the emulator, we have all of these changes that we just did, and we know that they all are passing because the unit tests confirm that everything's good. So notice here that we no longer have all these nested control structures, so the code becomes a little simpler as well. So these are all good things. So then we'll just write a refactor, simplified the assembler and emulator code. Good. So now we can go back to our list of instructions here, and maybe we can have a push and implement the majority of these functions. Not all of them, but at least the great majority, enough to implement most of the code that we would reasonably want to implement when we start writing large assembly language programs. So we'll start by implementing all the branches, and that should be easy. It's mechanical. The only real difference between all these branches is what they do, which is the predicate and the encoding for that predicate. So let's go back to our, and remember, all of our assembler functions have been implemented. So all we need to do is go to the emulator tests and find all of these branches. So here's a branch not equal. We've already done that or implemented that, and that works. Let's go ahead and copy that. Oops. And we'll use that for our next implementation. That's branch greater than. Here's branch equal. Okay. So let's take the the test for not equal. And what did we do here? So we initialized the register 4. So we're adding 0 on the immediate value 1 to the register 0 value, which is always 0. So we get a 1 in register 4. And then we compare that with register 0, and that should not be equal. So in this case, we want to change this. So we'll set the initial value of the register 4 to 0. Then we compare register 4 to register 0. Since register 4 has a value of 0, the jump should be executed. So there's our branch equal implementation. And then for the next one, branch less than, it's going to be very similar. Branch less than. So in the branch less than, we want to branch if the contents of register 4 is less than 0. So let's make the contents of register 4 minus 1, or actually minus 2. There we go. And then we expect register 4 to have the value minus 2. Oh, we should probably change the branch equal one so that it has 0 in register 4 at the end of the successful test. Good. That was BLT. Now less than unsigned. This one's a little bit more tricky because now we can't use the 0 register because there is no number that is less than 0 in the unsigned world. So what we'll do is we'll add another statement. We will say that register 3 has the value 2, and then register 4 has the value 1. Now 1 is less than 2. So let's make this even more interesting. What we'll do is we'll make the register 3 have the value minus 2. And remember that minus 2 is the same thing as this number. That's the bit pattern for minus 2 in 2's complement. And because we're treating this bit pattern as an unsigned number, it will be treated as the large positive number 2 to the power of 32 minus 2. This is what this number is. It's 2 to the power of 32 minus 2. So this is very definitely bigger than the 1. So if I compare 4 to 3, register 4 to register 3, I should get a true predicate, and we will branch to the end of the code, and then the value inside register 4 will still be 1, and so this test should also pass. And greater than or equal, well, it's going to be very similar. Oops, I think I've lost my clipboard contents there, so we'll just grab this unit test. Okay, so here we want to change this to BGE, which is greater than or equal to unsigned. So here again, we want to make sure that register 3 is larger than register 4. Does that make sense? Yes. So because register 4 is a very small number, an unsigned number 1, and the register 3 is that large 2 to the power of 32 minus 2 that we saw before. In this case, we then should have the result in our register. Oops, and we need this as well, don't we? I'm a little sloppy here. I'm a little rushed. Let's take it slow and get everything right. Okay, so here it is. So at the end of this, we expect register 4 to have still the value 1. Nice. Okay, so we have now the implementation. Now let's get rid of these ignore directives so that our tests actually get executed. And let's try running this. And we should get an exception now because we haven't actually implemented these. Oh, that was unexpected. Where are our errors? Did we already implement them in our emulator? I don't think we did. Well, this is interesting. So, I think we need to reload our tests and run them all. Are we actually hitting them? Let's put a breakpoint in our emulator and see what actually happens. Something is not right here. Okay. So, also make sure the assembler is doing the right thing. BGEU. Yeah, that looks good. 111, which is the correct. Okay, so interesting. We'll have to debug this. So let's run our emulator. Oh, that was a mistake. Let's stop this. There we go. We finally have an error. That's what I was wondering about. Why are we not seeing the errors? So BEQ is not behaving as expected. And what's the problem? It's not implemented. Okay. Unknown func30. Great. So let's go ahead and implement. And we might as well implement all three of our branches at once because they're going to be very similar. So let's go back to our manual. The manual says that branch equal, BEQ, has the func3 of 3 zeros. So in that case, the predicate is equality. Source 1 value equals source 2 value. And then a break. And then for BLT, we need the bit pattern 100. That's our BLT. And that's a less than operation. And let's go back to the manual. For BGE we've done. Then we need BLTU and BGEU, the unsigned equivalents. So BLTU is an unsigned comparison. So here we have to cast the operators that we're comparing on so that they are treated as unsigned integers and not signed integers. And this is a less than operation. And then for the final one, BGU, then the predicate is again operating on unsigned values. And this is an important point. BGE is not the same thing as BGEU because of the way it interprets these numbers. So if source 2 value is a very large, or say the -2 again, in this case, if source 1 value had been 0, then 0 is larger than -2 because it's treated as an assigned number. But in the unsigned case, that -2 gets reinterpreted as 2 to the power of 32 minus 2, that 0x FFF FFFFE. And in that case, this equality would be, or this condition, this predicate would be false because that very large number is definitely not less than source 1 value, which would have been 0. So that should take care of all the branches. Let's run our tests to make sure that everything is good. Still unhappy? Not implemented. Line 349. You are lying, my friend. I think there's something. Let's reload again. As a general comment, my developer experience with Visual Studio Code hasn't been as great as inside of Visual Studio proper. I'm not sure why I'm seeing so many problems, but okay, so we're asserting now because oh, we have a garbage cut and paste error. So I'm not blaming this one on VS Code. This one's on me. All right, let's remove our filter and run everything again. Let's hope that we'll catch all of our branches now. All right, so let's take a look at our test results. Are you still unhappy? Why is that? Okay, now it is happy. Let's run all these tests now. Good, all of our branches are now implemented. Good. We've already done all the loads and the stores, so we can skip those. Then we have SLTI and SLTIU. I think we've done SLTI already. The set, if less than, but let's check that out. SLTI, there is SLTI. So SLTIU would be doing the same thing as an SLTI, but with an unsigned comparison. All right, so let's go to the unit test for SLTI. And this, oh, interesting. We actually haven't ever implemented it. Good, so we'll get to implement the unit test for this. So let's get rid of these ignore pieces first. All right, so what is this supposed to do? Well, it's supposed to set the destination register, in this case register, say 3, to the result of comparing the value of a particular register, in this case register 0, with immediate value. So if 0 is less than 1, we should get a 1 in register 3. And let's hope that that does the job. Okay, we introduced an extra brace there that we can get rid of. Okay. So that SLTI should work. Let's try running, because we already have an implementation for it, so we shouldn't get any errors if we run our tests now. But we should get an error for this one because it's not implemented. See, I'm not happy about this. I'm not seeing the changes propagating. Let's run them all again. I'm expecting an error because we have this assert fail here. Well, how do we fix this? We will have to find the SLTI. Oh, that's why we hadn't seen this before. SLTI false and true are implemented. Because we have them over here. I'd forgotten about this. Okay, so that means that our SLTI function is redundant. We can throw it away. And let's get rid of SLTIU, and let's just copy SLTI true and false. Now these two perform unsigned comparisons. So we'll have to review the tests here to make sure that we're truly testing unsigned comparisons. So we will do the same trick where we'll use -2. And we will put that here. Now, if I do a less than comparison of 4 and -2, and the -2 is treated as an unsigned number, then SLTIU would fail. But in this case, it will succeed because it's being treated as an unsigned number. All right, let's do the same thing for the false case. Here we don't want to see any changes if this number exactly. As after this will not be less than, so we will get a 0 in register 4. Okay, let's run our tests. And we should get an error now because we haven't implemented. Yeah, see, I'm not sure where we're seeing this behavior. Please run. Okay, there we have the failure. And let's run this one as well. Excellent. Okay. So we don't know what func3.111, that would be the SLTIU. So let's confirm that. 011 is indeed the func3 for SLTIU. So what we'll do is we'll say SLTIU, and then its result is going to be if the source 1 value treated as an unsigned integer is less than the unsigned interpretation of the immediate value, then we have a 1, otherwise a 0. All right, let's try that for size. We should get an exception because we haven't implemented. Ooh, okay. What's the problem here then? Is it another? Yeah, okay, so let's make sure that SLTIU gets invoked. So we'll put a breakpoint in our emulator right about here, and then we'll run the test. Under the debugger. Let's go. Here we go. So func3 is 011. All right, so we have our source 1 value, which is -2, but if you convert that, did I switch the order of my operations perhaps? Let's take a look. We're comparing -2 to the immediate value of 6. Let's go to our test. All right. So let's put the -2 in. Let's make this the -2. Let's make that the number 5. We don't need this, it's redundant. We can just leave it there. It will get overwritten by the SLTIU instructions as it writes to register 4. Let's stop the debugger, and then let's try running all of our tests again. Let's clear the filter also. All right, let's go. Okay, I'm assuming that means SLTIU has been implemented properly. Okay, so then we get to this group of instructions, XORI, ORI, and AND-E, which are all immediate versions of XOR, OR, and AND logical functions, and which look grouped with the ADD-I instruction group. So this should be fairly simple to implement as well. So let's find Zori, Ori, and Andy. So how do we test Zori? Well, what we could do is take a number like well, this value. So 55555555. This is the bit pattern 010101, etc. 01 repeated 16 times. So if I take that bit pattern and I XOR it with the pattern of all ones, then all the ones in this bit pattern will become zeros and all the zeros will become ones. And so if I put the result in register 5, then at the end I am expecting that we get this back. And because of C# being C#, I have to tell it to please trust me. And then we want to get the contents of register 5. Nice. Okay. That was Zori. Now we have to find Ori. And Ori, what we could do here is we could set the higher bits. Well, we can do the same thing. Well, it's just a bit pattern. We'll take the same bit pattern. And then if we OR immediate with -1, then that's going to blast 1 bits all over this word. So the end result should be just 1 or FFFF. So we can check for that. So remember that the OR logical instruction is true if either one of the bits in the instruction is a 1, and in this case -1 is going to be all ones. So it's going to overwrite this word completely. Oh, good. And then well, let's see. Let's change the test slightly. We will take the immediate pattern that looks like this. 0f, just the last 4 bits are going to be true. And then all the other bits in the immediate operand will be zeros. And remember that if you AND 0 with anything, you get a 0. So it will clear the upper and now I just got disconnected there, so I'll just repeat what I just said. We're initializing our register 4 with this bit pattern, which is alternating ones and zeros. The AND immediate value that we're going to be ANDing with are the last 4 bits, the least significant 4 bits, are going to be all ones. FF is for all ones. But the remainder of that immediate is going to be all zeros, which means that this will mask out everything except the lowest hexadecimal digit, the 5 that we see here. So the end result should be 5. So let's write the assert. All right. So now if I run this, again, I'm expecting unit test failures because we haven't implemented Andy, Ori, and Zori yet. And there they are. Okay, great. So let's go ahead and implement them, and we might as well implement them all at the same time. So we will copy Addy, and let's go to the manual to see which. So the first one is XOR I, and we want 100 as our funct3. So this is XORI or XORI, and we use the XOR operator for that. And then we'll copy and paste that. We'll use ORI, which is 110. So now we use the OR operator for that. And then finally, ANDI, we will take the AND operator. Nice. Let's run our unit tests now, and hopefully we've written them correctly. All right, good. Next, we have a group of shift operations where we take a shift amount and shift it to the right. So let's find SLLI in our unit tests. There it is. So we're going to take a number and shift it to the left. Well, that's easy enough. Let's initialize register 4 with register 4, let's initialize it with the value 2, and if we shift it left by 1, then the result should be 2 shifted, so the bit pattern of 2 is 0, 0, 0, 0, etc., 1, 0. If we shift it to the left, that means poking a 0 in the beginning. This bit pattern is 4. So we expect that at the end of this operation, register 5 should have the value 4. All right, that was SSLI. Now shifting right, logical. We can just do the inverse here. We'll start by initializing this number to 4. Let's change the comment here. And then we shift right logical, and then the result should be 2. Nice. Next, for the arithmetic shift, remember that this is the case where we treat the number as a signed number, and so we need to initialize the number to a negative number, and the easiest way to do that is to just set, this is all once. Let's get rid of the comment. It's not really adding anything. So this sets up register 4 to have the bit pattern all ones, and then when we shift that to the right by 1 or 4, any number, then the bits are going to get shifted out on the right side, and then new bits coming in will be copies of the sign bit. But because the sign bit is -1, that means that the end result should also be -1. So doing an arithmetic right shift of -1 results in -1. So let's do that. Now we run out all of our tests, and we expect now to get failures because we haven't implemented these 3 operations yet. Yeah, see, this is so odd. Why are you not executing that? All right, so it's not unhappy because, yeah, we haven't implemented these shifts. So let's take a look at the func3 for them. It's 1 and 101. Ooh, oh, it's the high. Okay, so this is important to note. We need to make sure that we look at the high piece of the the func7 part. So let's take a look. Let's see where we have implemented this function. Okay, so we have to be careful here now. If the function is of type 001, then we have to check the func7 as well. All right, so this is something very special for shift. So if the func3 part is 001, then we have to extract the shift amount and then also the func7 part. So we'll do func7 equals bf func7 extract unsigned, and then we want the shift amount, which is the bit field that is starting at bit position 20, so what usually is called source 1, but in this case, well, we will say cast source 1 into an integer. Alright, so now we have our shift amount, and then we need to make a decision based on func7. So we'll do the same pattern here, switch func7. So if func7 is a 0, then we do a shift left immediate. So if it is 0, we do a left shift. So what we do is we say destination, actually, value equals source 1 value left shifted by the shift amount. And break. And then otherwise we need to throw an exception because it's an unknown func3. Or func7 actually in this case. Oh, what's going on here? Let's get rid of this. Nice, so we'll put that in here. That takes care of that case. And then we want to do something similar for the right shifts. So we go down to case number 5. And then the shift amount is extracted the same way. But in this case, when the func7 is all zeros, then it's a shift right logical. And so then we do this little dance where we actually C# implemented a new operator. There you go. That's an unsigned logical right shift. And then if the shift or the func7 is this bit pattern, then we are talking about a arithmetic right shift. So in that case, we do not do this. We do a regular signed right shift. And at the end of all of these, the value will be updated. Okay, let's run all our tests again then. And it looks like it ran them all and we're all happy. Fantastic. Then we have add and subtract. I think we've already done add and subtract. But let's just confirm that. We don't. We haven't implemented subtract. Can you imagine? We don't know how to subtract two numbers. So let's write code for this. So we'll initialize register 4 to have the value 2. And then we'll initialize register 5 to have the value 3. And then we subtract register 5 from register 4. So from register 4, subtract 5. And the end result, put it in register 3. And here we expect register 3 to have the value -1, because that's what subtraction does. So 2 minus 3 should be equal to 1. -1. Right, let's run this test. It should fail because it seems like we haven't implemented sub. Look at that. Indeed, we haven't. So, all right, let's find the implementation of sub. So sub is this number. And that's the funct7. Then value equals source1 value minus source2 value. Imagine we made it this far without even implementing subtraction. Right, there's happiness all around. Then we do the shifts. I think we've done SLT. Let's just go here and see. No, we haven't. Shift left logical has not been implemented. Set less than, that's a different thing. So let's start with shift left logical. So, and I'm assuming that's the correct interpretation. SLL. Let's make sure. We don't want to implement incorrect logic. I'm not a professional when it comes to RISC-V. I'm just an amateur, so I need to make sure that I'm not. It is a shift left logical. So we can safely proceed then. So shift left logical, what should it do? Well, first we need to set up a bunch of registers. Now in this case, this shift left takes its operands as registers, both of them. So we have to set up 2 registers. First, let's set up register 4 to have the value 2, and then register 3 to have the value 3. All right, so we take the number 2 and we shift it to the left by 3 steps and put the result in register 5. And 2 multiplied by 8 is 16, so we expect the result to be this hexadecimal 10. In register 5. So if I run that test now, I should get an error because we haven't implemented SLL. Nice, so we go there. And SLL has a funct7 part. So we have to do first the base case, which is the funct3. Case 1, and then switch funct7, and the funct7 part is all zeros. This is SLL, and then that case value equals source 1 value left shifted by source 2 value. Then we need to handle the case when we haven't implemented the opcode and we have to have a break for syntax reasons. Okay, let's run our test again. It's happy. All right. So now we have SLT and SLTU, which are going to be similar to SLTI and SLTU, except here we're comparing 2 registers instead of a register against an immediate value. So let's go to our emulator tests, and let's get rid of the NYI here. So in this case, we're going to set up so that the 2 registers Actually, we should test both the true and the false case. So let's use test case. Let's use test case using the value 2 and 3. 2 is less than 3, so here we expect a 1 in the result register. And then, and then here, why am I getting an error here? Right, so we have to say integer reg1, integer reg2, and integer result. There we go. So initialize reg1 with the value, actually, let's use the value 5, register 4. It should have the value in reg1. And the second register that we're comparing against should have the value in reg2, and then the result will be in register 6, and it will be the less than ness of 4 and 5, and then we say assert are equal result emulator registers 6. So what we've done here is we're using an NUnit feature that will pass in our first case, a 2 into register 4 and a 3 into register 5. 2 is less than 3, so we expect SLT to put a 1 in register 6. But if we switch the order, then it's no longer less than. In fact, let's make them equal. That's still not less than. And in this case, we should get a 0. Let's run SLT and see whether that indeed proves to be the case. What happened to our tests? They just disappeared. They're down here. Okay. Let's run those two cases. Okay. And it's failing because, yeah, we haven't implemented SLT yet. So let's do that. Now SLT is... we got... let's see, we got an exception. On what line? 165. So we haven't implemented funct10. So case 10. Is that correct? SLT 10, yep. And it has a funct7, which is the all zeros pattern, and this is SLT, and the value is 1 if it's the source 1 value is less than source 2. Otherwise 0. Let's run those two tests again. Everything's happy. SLTU is the unsigned buddy of SLT, so we should be able to do the same thing here. So in this case, we'll have two unsigned numbers. So let's do it the following way. So here's our unsigned check. Let's just steal this code. And Let's cast these things to integers because C# is strict about this. Nice. Okay, so now we have SLTU. Where is SLTU? There it is. Let's run those tests. And we should get another exception here because, oh, we have implemented SLTU. Let's make sure that that is indeed correct. We have not implemented SLTU. Why are we getting a result? It could be that the copy and paste broke our tests. Let's try that again. Yeah, okay. So func3 now is 1, 1. So we do the same dance here. Let's just verify that we've implemented the correct. The func7 bits are all zeros, and the func3 should be 0, 1, 1. So that is SLTU. So in this case, we have to treat the values as unsigned. And that should do the job. Let's run all of our tests now. Okay, we still have a failure. Let's find out what that is. Okay, so we have a bug. We have the number 2 in register 4. We shifted to the left by 1 step. Okay, so we have to figure out why SLLI is not working correctly. Let's find SLLI. Let's put a breakpoint on this and then debug that. Let's get rid of this breakpoint. It's no longer needed. All right, so source value should be 2. The shift amount is 4. Aha, okay, so this is a case where we may have, yes, our implementation of the assembler is incorrect. So we need to fix that first. The assembler for SLLI or SLLI is not correctly implemented. So let's find SLLI. So the idea here is that op3 is supposed to go. Yeah, that does look correct though. Let's see how SLLI is implemented. I think that there may be a bug in the assembler. Okay, so it's using the R syntax, but that's not correct because this, oh, oh, this should be okay. Let's take a look at the actual test. So if op3 is 10101, that's the result we see there. So are we actually executing SLLI? Let's go back to the emulator tests and look at SLLI. That should be a 1. Well, let's take a look at the assembler then for SLLI. Right there. And let's go back and run our code. Not hitting the assembler the way I expected. Do that again. Yeah, let's disconnect. Go back and run that again. Okay, so our destination register is 5, our source is 4, and the shift amount is 1. Let's go inside. So we're supposed to take our shift amount and shift it to the right by 20 bits, which is indeed what happens here. Okay. Alright, so the assembler part seems to be okay. Now we hit the execution part. That's the add I. We know that works. And then SSLI or SLLI is executed. And there's our bug. It should be source 2, which we haven't extracted. So we need to extract source 2. Var source 2 equals bf source 2 extract unsigned. Okay, that was subtle, but in the end we caught it. Let's see if we can now get that to pass. Okay, SRLI is also failing, probably for the same reason. Yeah, for exactly the same reason. So let's just grab the code here. And then run our test. And now hopefully everything should be hunky-dory. And now the debugger is confused. Let's just restart everything. Visual Studio Code is freaking out. Let's just close the shell and restart it. I'm not sure why it bailed out like that, but let's just run all of our tests. And we no longer have any failures, I hope. All right. We'll just do a few more of these, but then in the interest of sparing time, well, yeah, we have these 5 more. XOR and SRL and SRA and OR and AND. Let's do those, and then let's call it a day. There's plenty more to finish up with, but a lot of them are floating point numbers, and we haven't talked about floating point numbers yet, so we'll save those for another session. But let's do SRL and XOR and friends. So find XOR So XOR is the same idea here as before. We will have a bit pattern. We'll put we'll put in register 4 the value AAA, and in register 5 we'll put the bit pattern FFF, and then XOR, put the result in register 6, the result of XORing register 4 and register 5, and so this will flip all the bits inside of the AAA, so that instead of AAA we'll get a 555. That's XOR. Now shift right logical. Simple enough. We need to set up a register 4, which will have the value 6, maybe? Let's do that. And then register 5 will have the value 1. And if I shift register 5 to the right by 1, I should end up with a value 3 in register 6. Because 6 is the bit pattern 110, and if I shift that to the right by 1 step, the two 1s end up being there, and that is a 3. Good. And then shift right arithmetic. Now we have to come up with we'll do the same thing we did before, where we take the value of -1, and regardless of how many bits we shift it, that value will remain -1 because the sign bit gets propagated. So let's do that. So regardless of how many times we shift it to the right, here we're shifting it to the right 10 steps, doesn't matter. The most significant bit is preserved, and we end up with -1 regardless. Okay, let's we could even start with -20, which is a bit pattern that starts with a bunch of 1s, and so if we shift out 10 binary digits, then the result is going to be all 1s. All right, that was SRA, and then we have OR and AND. Okay, so OR and AND are easy. We will get the bit pattern so in register 4 we will put the bit pattern, well, AAA, I guess, and then we do an OR with a register 5, and in that register we'll have the bit pattern 0F00, and the F will overwrite all the bits, because ORing, if either of the bits is 1, then the result is 1, so this high nibble here will become F, but the other ones where there's a 0 ORed with it, ORing anything with 0 leaves the initial value untouched, so the A's will remain A's. So the end result is, and of course we have to put that in register 6, the result of ORing 4 and 5, and the result is going to be 0xA, Actually, let's change that digit to the middle one, because I want to avoid sign extensions, but this should be the result then. In the emulator register 6, and then our final instruction for today is AND. I'll just grab the whole test here. Change the operation to and so in this case, the F will mask through, so it will leave the following, remembering that the AND operation requires both operands to be ones. So if there are any 0 bits involved, the result will be 0. So this 0 here will mask out the A, so will this 0, but this F will keep the bits of the A. So the result should be this. Let's run all of our unit tests. We're going to get exceptions now. Yeah, see, it's stubborn. Well, let's find AND. You haven't actually run it, my friend. Nope. We really have to run that specifically, don't we? Oh, we're dealing with an error. There is a syntax error. What's this? This missing semicolon. Maybe that's the reason why I'm having trouble. I'm not seeing the errors clearly. Here we go. So AND is down here, and it has a funct7 of all zeros. So we grab this. We copy it for AND, which was 111. And we change it so that the operation that we carry out is the AND operation. And I assume that OR will have its own funct3. Indeed it does. So we can change that to this value, and in that case, this is an OR. We implement OR. And, all right, let's run what we've got. Okay, we haven't implemented XOR, which is function number 4. That goes here. And then XOR is implemented like that. And then we have shift right logical and shift arithmetic logical. This is 101. So we will sure that shift right logical is indeed 101. But then the funct7 part will be 0. But then if it's arithmetic, it's got this funct7 part. So let's go ahead and slap that in here. And this would be shift right logical. So when we're doing right shifts that are logical, we have to treat the value as an unsigned value. And again, we can use this new feature in the C# language. And if it's a signed or arithmetic shift, then we use this operator. And let's make a comment to that effect. All right. Do we think everything will run now? Let's give it a try. Okay, still not happy. Unknown funct3 101. Yeah, see, this is the weirdness. Okay, so now it's not happy because my mistake. This should be, we want to shift register 4 by register 5. And the same thing here. Let's run those tests. Okay, now it's only OR. So, right, we have a sign extension problem here. Let's just change this one to be 2. Then this should also be 2. So I'm a little tired now and I can't really do this math in my head, but it's a sign extension issue. Okay, so now we have unit test passing. So as you can see, this is a fairly mechanical piece of work at this point. There's still over 100 instructions. A lot of them are, as you can see, floating point instructions. You can tell because they all begin with an F. I'm not going to do those today because we haven't discussed what floating point numbers are, but I will in the future. But in the meantime, review this code and think about what instructions you would like to see implemented in the emulator. And what we'll do is we'll continue next time, again, building towards writing a pretty large, substantial program in assembler language. Until then, I hope you have a great time and see you again soon.